Okay, we're going to look at the first problem in section 6.4, which is on the shell method. We're going to find the volume of a solid by rotating the region underneath the graph of 6x cubed, this cubic function. We're going to rotate about the y-axis, and it's the region that's on the interval from 0 to 1. So underneath this graph, and really above the x-axis on this interval from 0 to 1. So I graphed this function. Here's the 6x cubed function on the interval from 0 to 1. This sort of region right here is what we're talking about. And we're going to actually rotate it now about the y-axis. Okay, so we're going to come this way. And as we rotate that, this region is going to come out of the page back in and circle around. And we're going to get this solid. On the outside, it looks like a cylinder, but if we look from the top, there's like a bowl region here, right? This is forming a bowl. So this is some like a fancy water bowl for your dog or something. I don't know. Any rate, we're finding the volume actually of the solid portion of this, right? So the cylinder taking out that bowl shape, what's left over, what's that capacity or volume there, not the capacity inside the bowl, right? We're finding this the volume of this solid. Okay, so how do we do that? Well, you could use the disk method, but you would have to integrate with respect to the y-axis there, so that we would be looking at horizontal rectangles and rotating them about the y-axis this way, and we would actually get washers there. We could do that, but you'd have to solve this function. Y would be equal to 6x cubed. You have to solve for x as a function of y. Bottom line is shell method is a little bit quicker in some sense in this problem. I'm going to integrate with respect to x from 0 to 1, and we're going to take this arbitrary rectangle, which notice is at an arbitrary distance x from the y-axis. Remember, the y-axis is, of course, x equals 0. So we're going from x equals 0 to x equal 1. And I'm going to rotate this rectangle. It's going to go back into the page over here, and we're going to form this thin cylindrical shell, right? And we call this the shell method. So the y-axis is here. And the height of this shell is just the height of our rectangle, which notice this is the curve of the function f of x equals 6x cubed. So h of x is just 6x cubed, right, as x varies from 0 to 1. And then I call this p of x. It's the radius from our axis of rotation to where our rectangle was, right? And that's just this length, which is just x, right? Whatever x is, as x varies from 0 to 1, that will be the radius. And so if you remember, here's the formula for it. Where does this come from? 2 pi p of x h of x is the area of that we're integrating from 0 to 1. And where do I get that from? Well, if I sort of cut open this thin shell and unroll it, I'll get a rectangle, right? The height will still be 6x cubed, and the length will be the circumference around this circle, which is 2 pi times the radius, which is x. And so this is p of x, this is h of x. That's why it's 2 pi p of x. Sorry, this is 2 pi p of x here, and this is h of x. And that's why we have that formula to find the area, because this is just a rectangle, right? Length times width, if you will. And so I'm integrating, of course, from x equals 0 to 1. So p of x, again, is the x, and h of x is 6x cubed. I pull the 2 pi out. X times 6x cubed is 6x to the fourth. That's easy to find the antiderivative of. 2 pi times 6 is 12 pi. X to the fourth antiderivative is that, 1/5 x to the fifth. So I've got 12 pi, or 12 fifths here if I pull that 1/5 out, pi. And evaluating x to the fifth at 1 and at 0, of course, I just get 1. And there's my value for the volume in cubic units, 12 fifths pi, or you can write as 12 pi over 5, whichever. Okay, so hopefully this makes sense with the shell method. Again, it's very important to draw the region and then your shell in this case, or you're using a disk washer method, whatever it is, and clearly to help you really clearly set up the integral correctly. Okay, hope this is helpful.